So let us consider now this killing vector, 1, 0, 0, 0, which corresponds to time translations for the Schwarzschild spacetime. Then k mu times u mu is equal to u0, which is g 0, 0, u0. Remembering g00 component of the metric is just, well, remembering what is the g00 component of the Schwarzschild metric, this is just 1 minus rg divided by r times, and u0, I remind you because it's, well, in this coordinates it's dt over ds. So this is u0 and this is g00. So this is a conserved quantity. We will denote it as E divided by m, as E divided by m. The m is the mass of the particle. E, we're going to explain that E is energy, but at this moment one can say that from the, according to the Noether's theorem, every symmetry has as a consequence a conservation law. So the fact that this quantity is conserved is a revelation of Noether's theorem. And one knows from the classical physics that from the time translations, it follows that the energy is conserved. So this is one of the arguments that E is energy. But below we're going to see further, a bit more arguments why E is energy. So another killing vector that we have in Schwarzschild spacetime with upper index is just 0, 0, 0, 1. And corresponding conserved quantity, as follows from the same observations, is just r squared times sine squared theta d phi over ds is conserved. So we will denote it as L divided by m, where m is again mass and L is going to be angular momentum, as follows from the rotational symmetry, follows the conservation of angular momentum. But we're going to see a bit more arguments why L is momentum. So now, to move further, let us observe that this is nothing but the Kepler's law, basically, one of the Kepler's laws. Because in fact, well, a relativistic variant because we have here dividing by proper time rather than coordinate time. But the Kepler's law says that if we have a planet and its radius vector during unit time covers equal areas are covered by the radius vector of the planet. So this is exactly radius vector of the planet, as one can see. And from this observation, in analogy with the situation of non-relativistic situation, we can understand that that the motion of the particle with mass m goes in one plane, which means that we can fix theta, and we're going to fix it to be at pi equals over 2. So which means that the motion goes in the plane defining in the space defined by the equation x3 equals to 0. And as a result, this conservation law has the following expression: r squared d phi over ds is equal L over m. So we have these two conservation laws, this one, and this one, and going to use it now. So remember that for a motion in for the four velocity vector, we have the following equality: 1 is equal to g mu nu dz mu over ds dz nu over ds. Well, just because in the denominator we have ds squared, and in the numerator we also have ds squared. That's the reason this is 1. So this is ds squared, which means that g mu nu times u mu times u nu is equal to 1. Now, using this for the Schwarzschild metric, let me remind you that the Schwarzschild metric has this form. Metric tensor has this form. It's 1 minus rg divided by r minus 1 minus rg divided by r. And also, of course, here we have r squared, and here we have r squared sine squared theta. So this is a metric tensor. But we also take into account that this part doesn't participate because in our case theta is constant. Hence d theta here in this expression, d theta is 0. So using this metric here, using the expression for the 4 velocity, and the fact that d theta is 0 and theta is equal pi over 2, we have the following equality. 1 minus rg divided by r dt over ds squared minus dr over ds squared 1 minus rg divided by r minus r squared d phi over ds squared. So this is equal to 1. This is equal to 1. Now, using this conservation law and this conservation law in this expression, we obtain the following equation, that dr over ds squared is equal to E divided by m squared minus 1 minus rg over r times 1 plus L squared divided by m squared r squared. So this is the equation for the geodesic. This is the equation that we have been looking for. But to understand the physical meaning of E and L, let us take the non-relativistic limit of this equation. So what means non-relativistic limit? Non-relativistic limit, first of all, is that Rg is much less than R, so we are very far from the gravitating body. And velocity, dr over dt, is much less than 1, much less than the speed of light. In this limit, it can be seen that dr over ds is approximately dr over dt. Well, actually, better to say that this is much less than 1. So then this is equal to. As a result, in this limit, if we take this limit in this expression, we obtain the following equation, that E squared minus m squared divided by 2m is approximately equal m over 2 dr over dt squared plus L squared divided by 2m r squared minus m times rg divided by 2r. So let us look more closely to this equation. Let us look closely to this equation. And this thing, in the limit that we are considering, again in non-relativistic limit, is nothing but E squared minus m squared is equal to E minus m times E plus m. And it is not hard to see that in the non-relativistic limit that we're considering, this is approximately is 2m, and this is approximately E, which is kinetic energy. Kinetic energy. As a result, we have a product of this times this divided by 2m. This is nothing but approximately non-relativistic kinetic energy E standing here. So this equation is nothing but non-relativistic expression that we know in standard non-relativistic mechanics for the motion in Newton's potential. This is because exactly expression for the Newton's potential, because I remind you that this is nothing but 2gm, where 2 kappa, sorry, m, where kappa is Newton's constant and m is the mass of the gravitating body. And 2 is cancelled, so this is just Newton's law. This is just kinetic energy. Sorry, this is a total energy rather than kinetic energy, I'm sorry. Non-relativistic total energy. And then this proves that L, another way to see that L is, which is here, is angular momentum, and E, which stands here, is nothing but the energy. Nothing but the energy. So we have everything at our disposal, that, remember that this is much less than m. So anyway, we have everything at our disposal to go further with the solution of this equation.